Well, thank you for coming Friday morning for this seminar today. We should be beginning in about a moment or two, but let's see, I'll wait for the red light to come on. Please be aware of the exit signs, because if we need to vacate, we have to go through those doors in case we need to leave the building or whatever it may be. Okay, the webcast is on, and we encourage people that are on the internet for the Q&A to send your email questions at first opportunity so we could have time to take them on the air. So with that, Dr. Lashgari.
Good morning. Today's topic is about biogenic emissions, and we are truly privileged to have one of the premier minds on atmospheric chemistry in the state, Professor Alan Goldstein, and to hear a little bit about the work that was done in a project called CABERNET. I don't really need to say very much more about Professor Goldstein. A quarter century of research, several hundred peer-reviewed papers, and graduating probably a phalanx of premier scientists. What else can you say? Professor Goldstein.
Thank you, Ash, for the very, very generous and kind introduction. It's really a pleasure to be here at the Air Resources Board. I see a lot of familiar faces in the room, and perhaps some familiar faces online too. So today, I'm going to be talking about a project that we did to measure isoprene fluxes over the state of California. It was a very exciting and very ambitious project, and I really want to thank the Air Resources Board for giving us the opportunity to do this, because when we started the project, there was some risk involved because it was untested sort of technology and approach. But we teamed up with people from my group, and in particular Pavel Nistal, who's here in the front row. Pretty much all of what I'm going to show today is fundamentally his work. So that's why his name is a little bit bigger than everybody else's on the introductory slide. Also, we worked very closely with Alex Gunther, who was at that time at NCAR and is now at Pacific Northwest National Laboratory. Tomas Karl, who is also at NCAR but is now a professor in Innsbruck, Austria. And then Haf Johnson and the team from the Naval Postgraduate School SERPAS group. And then we worked very closely with Klaus Scott and Jeremy Apice here at the Air Resources Board on the modeling side. So thank you to all those folks. I know I don't need to remind this group, but I'll just say it anyway. The motivation for doing this work is simply that California is challenged with some of the worst ozone nonattainment areas in the U.S., and those are located largely in the Central Valley of California, the South Coast Air Basin, and that's true for ozone. It's also true for PM 2.5. And when we think about what's leading to those high levels of particulate matter, I want to talk about just for a moment. We know that we know something more than we knew about 10 years ago with regard to how much of the aerosol is primary and how much is secondary. And what we see on a global basis is that most of the organic aerosol is actually secondary, not primary. We've also seen that in a number of CARB-funded studies, like the CalNex study and the SOAR study from 2005. CalNex was 2010. In all cases, when we've done analyses in the summer of where the organic aerosol comes from in Bakersfield and Riverside in Pasadena, most of that organic aerosol is actually secondary, not primary. And so that means it's being formed from organic gases that are emitted. Isoprene and terpenes are the biogenic ones, and then all sorts of anthropogenic hydrocarbons as well. And so I want to point that out as a motivation, because a lot of the field right now is focusing on many of these processes about how the VOCs actually get transformed. But what we wanted to focus on in this project is whether we've actually got the input right, whether we've got the emission inventory right. And so as we think about that, it's important to differentiate between anthropogenic and biogenic sources of volatile organic compounds. Again, on a global basis, the anthropogenic VOCs are estimated about 100 teragrams of carbon per year. The major sources are mobile sources, transportation sector, fossil fuel, fire, solvents, paints, many other things. And then there's all the biogenic sources. And the biogenic sources on a global basis are estimated at about 1,150 teragrams, an order of magnitude more than the anthropogenic sources. Isoprene is the dominant one. And so you can see that isoprene here is estimated at 500 teragrams of carbon per year. So on a global basis, it's more than a third of the total emissions. And for that reason, in this project, we focus very much on isoprene and seeing if we've got the inventory right. And in particular, in California, the relative contribution of anthropogenic VOC and biogenic VOC is poorly constrained and very significantly among different air districts. And so that leads us to the motivation. Vegetation in California comprises a large source of BVOC, which react with anthropogenic pollutants and contribute to photochemical ozone and particle formation. In many regions, isoprene is the most important VOC affecting regional air quality, and the vast majority of isoprene emissions are expected to occur from oak trees, which cover about 7% of the land surface here in California. And it's also regionally specific, as I'll show you. The previous biogenic VOC measurements from California oak woodlands were made almost exclusively at the branch and leaf levels, and those measurements go back to the late 80s and early 90s. And there'd been essentially nothing done in California since that time on emissions from the oaks, but yet we know isoprene is the dominant VOC emitted, not just biogenic VOC, but the dominant VOC, and oaks are expected to be the dominant source. So we needed biogenic VOC emission measurements at the landscape scale in California to evaluate and improve the biogenic VOC emission models that are used for state implementation plan development. So that was why we did this. So I just want to broaden the perspective slightly to say that we've done a number of campaigns recently funded by CARB to look at biogenic VOC emissions. One of them that I won't really talk about much today was focused on emissions from agricultural crops. We did measurements from about 25 different dominant crops in California to look at the VOCs that were emitted. We found that almost none of them emitted isoprene, and that the emissions were relatively low, actually. And the dominant emissions we thought were likely from citrus, and so we went out into a citrus orchard and we did flux measurements for a full year. Those papers are all published. The report is out. But if you look around the valley, what you can see in green is the oak woodland distribution. And so those are expected to be the major isoprene sources. And in Cabernet, this is the project we're talking about now, we measured fluxes from the aircraft, and those red lines show you where we flew. So we tried to cover all of the major isoprene emitting, dominant isoprene emitting areas. Also at the end, I'll talk a little bit about some measurements that have been done at a tall tower, the Walnut Grove Tower. It's 525 meters tall. It's about 20 kilometers south of here. And because it's so tall, it actually allows us to get measurements of concentration that give us a more regional picture. Okay, so, and those measurements were done continuously for a year. But again, I'll just refer to those briefly. So one more picture. This is a picture that was taken where the star is. You can see there's a flux tower in the picture right about here. And that flux tower is the Tansi Ranch flux tower that Dennis Baldacci runs. They're not doing isoprene flux there. They're focused on carbon, water, energy, and they're doing some other greenhouse gases. But we did a few flux measurements with an REA system during this study at that site. And in fact, you can see Alex Gunther if you look really closely in this picture right there. There's Alex. He's there to run the REA system. He had his hands on the instruments. And this is actually a view from the aircraft as we flew over. So this gives you an idea of when the aircraft flies, what it sees in terms of a typical oak woodland in California. So this is a sort of rolling hills with oaks distributed over the landscape, and it's a grassland. But this is a typical very high isoprene emission region in California. Okay, so CABERNET was the California Airborne Biogenic VOC Emission Research and Natural Ecosystem Transects campaign. We named it CABERNET for a number of reasons. One of them is that my hobby is winemaking. Another is that this is really about the oak trees. And if we think about what we do with our Cabernet once we make it in California, we tend to put it in barrels of oak. And so there's a nice connection there. There are a lot of reasons for this, but anyway, thanks for letting me name it that. Nobody at ARB said I couldn't. There have been two papers published so far from this study. I'll be referring to them. One, Thomas Karl was the lead author on, that was published in Journal of Atmospheric Science in 2013. Another was by Pavel Mistal, and that was published in Atmospheric Chemistry and Physics in 2014. And there's another paper that's in review. Okay, so you can see in this picture actually Thomas Karl, there's Pavel, Abhinav Guha contributed quite a bit from my group, who was focusing more on some greenhouse gas measurements, and there's Alex Gunther, and then Steve Schertz from NCAR, who did a lot of technical support for us. Okay, so what were our objectives for the CABERNET campaign? It was to evaluate airborne VOC flux methods on the regional scale. Again, this hadn't been done before. Isoprene fluxes hadn't been measured before on a regional scale, so we had to test our methods and make sure that we were getting it right. We were going to investigate the vertical transport of isoprene in the planetary boundary layer, and that was necessary actually to interpret the flux measurements made at aircraft altitude to infer the actual emissions at the ground. And then we were characterizing the land cover effects on isoprene emissions, and really the main point was to verify and improve isoprene emission models that are used by the Air Resources Board. So in order to decide where to fly, we had quite a lot of work up front to do. And one of the main things that we tried to do was to compare existing emission models and look for where there were discrepancies. And so this map is showing you the difference between the Megan 2.0 model, which was a biogenic VOC model that was developed by Alex Gunther at NCAR and is used broadly, including by the EPA, and the BEIGIS model, which is the California Resources Board's in-house model for biogenic VOC emissions. And what you can see here is that there are areas where they disagree. And so we tried to focus on those areas. We also wanted to focus on areas that had relatively flat terrain because it makes the flux measurements easier to interpret, but that's hard when all the oaks live in the hills. So we were really flying mostly over the foothills and over flat areas, but the flux measurements get harder to interpret when we get into steeper slopes. And then we were also trying to fly over the regions where we had expected high emissions from the oaks, and in fact, that's what we did. And so here we're showing the GAP database for where the oaks are in green, and where our research flights were. So the research flights are labeled RF1 through RF8. There were 8 separate flights. We had a total of 40 hours of flight time, and we used that to fly approximately 10,000 kilometers over California. Most of the flying was done at 400 plus or minus about 50 meters altitude, so we tried to stay fairly constant altitude most of the time. The payload for the plane included a proton transfer reaction mass spectrometer, which we used to measure VOCs, and this instrument was actually borrowed from the National Center for Atmospheric Research, and it was based on a quadrupole mass detector, which means that we had to choose which masses that we were going to look at any given time. And so we could only look at about 4 masses at the same time, 4 or 5 masses at the same time, if we wanted to get high enough density of data temporally to actually calculate the fluxes. And so we always measured isoprene and then the sum of its isoprene oxidation products, NBK methacrylin. We pretty much always measured methanol and monoterpenes, and occasionally we'd throw in another species. Like if we knew we were going to fly over an area where there was a lot of oil and gas production, we put toluene into the measurement mix that we were going to focus on. Also, we had a Picaro analyzer for methane and CO2 that was loaned to us by NOAA, and that was Tom Ryerson and Jeff Peischel. They were very kind to let us use that instrument. And then we also put on a couple of ozone instruments, and we had a variety of wind and micrometeorology and radiation measurements that are part of the normal payload that the Surface Twin Otter uses. So this is the Surface Twin Otter. It's older military aircraft. It's run by at the Naval Postgraduate School, so all our flights took off out of airport there. It's right near Monterey. And you can see that it's a twin prop airplane, and we're getting ready for the flight. You can see we've got some gas cylinders down there. We're calibrating things. A couple features that I want to point out that, on the nose of the plane, there's a three-dimensional wind sensor, and then this inlet is where we're actually sampling gases, and so the gases are flowing through that tube, and then we're subsampling from that tube with instruments that are inside of the aircraft. The aircraft has room for a pilot and a co-pilot and 2 scientists, and then a limited number of instruments. Okay, this was a video that apparently isn't going to work for us, but it's still worth pointing out that this is the view we get from the aircraft. And one of the nice things that we actually added just before we flew is we decided to buy a very nice video camera that had a GPS locator on it. And so we have video through all the 10,000 kilometers of flight, and we can correlate that video with the trace gases that we see. So as we fly over something, we can see exactly when we get into the plume of whatever we're flying over. So it's actually really, really useful in thinking about the data, and there's an enormous amount of data mining that could go on in looking at this. This was going to show you flying into a little biomass burning plume and seeing all these tracers rise together very beautifully. Okay, so this is sort of a summary of concentration data that we got. This is isoprene. I want to point out that all the flights that we did were done at midday. We generally took off about 10 a.m. and landed about 4 p.m. The reason for doing the flights in midday is that isoprene emissions turn off at night. Our focus was on isoprene emissions, so isoprene emissions depend on light and temperature, and we'd expect the light dependence to be minimal in the middle of the day, and that's also when we get, because that's when light is highest. So we wanted to fly when the temperatures were highest so that we saw the higher emissions that really matter for air quality. So we flew 10 a.m. to 4 p.m. You can notice already in here that the blue is where we had very low isoprene concentrations, and every time we flew over the Central Valley, we saw extremely low isoprene concentrations. And then when we got over the foothills where the oaks are, you could see higher isoprene concentrations. You start getting into the green, yellow, and red colors, also over the hills in this region, up through the East Bay, South Bay and East Bay, and then up into Marin and Humboldt counties. You can see lots of oaks giving us lots of isoprene. Okay. MBK methacrylin are, again, isoprene oxidation products, and they had a fairly similar distribution to isoprene because isoprene has a lifetime of about 30 to 60 minutes in the atmosphere, so its products are produced fairly quickly. But one of the interesting features is that you can see that downwind of the isoprene sources, the MBK methacrylin are higher, and a really good example of that is up in this region. The oaks are really here where we flew over, and then as we go downwind towards the Blodgett Forest research site where my group did measurements for a decade or more, you can see that the isoprene oxidation products are prevalent, and there was less, I went the wrong direction. You can see that isoprene is not as high there, but the isoprene oxidation products get high downwind. Okay, and so that ratio of isoprene to MVK and methacrylin decreased as we got downwind of sources and as we went up in altitude. Another interesting molecule that we measured continuously, that it wasn't really the focus of the CABERNET campaign, but it was one that we knew might be important, was methanol. And methanol is important because it's actually the highest concentration VOC in California. It's much higher concentration than isoprene. It's less reactive, but it's very indicative of certain kinds of sources. And so one of the things that you see is that over the Central Valley, we did have regions where there was very high levels of methanol. And it turns out that the really high levels of methanol here were over the dairies and cattle operations that were in the Central Valley. And methanol is a good indicator for those emissions. And along with methanol comes lots and lots of other VOCs. And so this is kind of a useful thing to look at. Also, methanol has a much longer lifetime in the atmosphere, on the order of a week. And so it blows downwind of its source, and you can see it piling up at really high concentrations on the eastern edge of the valley, not because there are high emissions there necessarily, but because the emissions throughout the valley are coming and building up against the foothills. Okay, so we might come back to that a little bit later. And then monoterpenes. So monoterpenes, they're very reactive and relatively low abundance, and so they were very challenging to measure from the aircraft. We didn't try to actually turn these data into fluxes, but you can see where their distribution is. And basically, we saw very low terpene monoterpene concentrations through most of our flights, except for a few areas when we were over mainly pine forests and it was relatively warm, like up here near Blodgett, and in some areas up here in the north. But generally, there were relatively low abundance, although there is some as we fly over the Central Valley. And one of the things we found from the crop emission study that I mentioned is that the two dominant things that were emitted from crops were really terpenes and methanol. Okay, so from the valley we might expect those things. So that was the concentration distributions. Let's talk a moment about how we do flux measurements. So Airborne Eddy covariance is our method for doing fluxes. Basically, the flux is equal to deviations in the vertical wind speed that are correlated with deviations in the concentrations. And so we need a fast response measurement for wind and for the VOC concentrations. On the left, we're showing a couple instruments that would be typical for the ground. This is a 3D sonic anemometer that's measuring wind in all directions, but we're just using here the vertical wind speed, and this is a proton transfer reaction mass spectrometer. For the aircraft measurements, we were measuring the vertical wind and all the winds actually with sensors. They're pressure sensors that are on the front of the plane, and from the pressure differential you can calculate the wind. And then the PTRMS was built into an Airborne package that had to meet very, very rigid specifications. And anyway, I won't go into a lot of detail on that, but that's the PTRMS. The other thing that's interesting, as you can imagine, flying the plane, you have to be able to correct for the speed of the plane when you're trying to interpret the fluxes. And so that means that we actually have to subtract the vertical and horizontal motions of the plane. And in order to do that really well, we have to calibrate that. And so the way you calibrate the wind sensors is you actually go and do some really crazy maneuvers with the aircraft over the ocean. And you go up and down really fast. And they're referred to as the Lenchow maneuvers, or as our team often referred to them, they were the puke maneuvers. And you can ask Pavel about that in more detail, because he was on the aircraft for that. I was not. Okay. So the general rule, though, to get good flux measurements is to fly low and fly slow, and actually to keep it steady. So you want to keep your altitude and your speed as constant as you can. Okay. So we actually use two approaches to calculate the fluxes. One is the classic approach of fast Fourier transform, where you take the data from a long segment, let's say 100 kilometers, and you look at the covariance between the vertical wind speed and the concentration, and you're looking at the deviations from the average in this case. And so you're averaging the concentration, you're averaging the vertical wind speed over 100 kilometers, and you're looking at the deviations over that whole segment. that gives you one value per transect. We tried a new approach that had never been used for regional isoprene fluxes before. It had been used one other time for VOC fluxes over Mexico City by Thomas Carl and his team. But it was called the continuous wavelet transformation. So it basically gives us a higher spatio-temporal resolution that we believe actually gets us fluxes that are meaningful at a spatial scale of 2 kilometers. Okay, so this is the difference between those two approaches. The blue is the fast Fourier transform, so we get these averages over some transect, and the wavelet fluxes in the red give us the variability, and you can see they actually average to about the same, and they were very, very good agreement, but these wavelet fluxes were instrumental in allowing us to check the spatial reliability of the models, right? So if we had to look at VOC emission models averaged over 100 kilometers, we wouldn't learn as much as if we can look at them averaged over 2 kilometers. Okay, so another thing that we had to do to figure out the flux at the ground is we had to look at what does the vertical flux profile look like. And so in a couple of locations we did what we call racetracks, where we flew the same over the same exact landscape multiple times at different altitudes, and we measured the fluxes and looked for vertical flux divergence. And so you can see that here we did the same racetrack over and over again in 2 different locations, and we measured fluxes at 700 meters, 850 meters, 1,000 meters, 1,200, 1,400 meters. Basically, we did it all the way up to the top of the boundary layer, and then we looked at the decrease in flux with altitude. So how do we use that? So it turns out that as you can imagine, as isoprene's emitted at the ground, and it gets up to where we're measuring the aircraft, as you go up in altitude, the flux is decreasing because isoprene's actually reacting with hydroxyl radical. That's why we care about isoprene, because it reacts fast with hydroxyl radical, it makes ozone, it makes particles. So from that vertical profile fluxes, we can actually get 2 critical pieces of information. One of them is that slope in the fluxes with altitude is basically due to the loss of isoprene. The loss of isoprene is a rate constant that we know, the isoprene concentration that we're measuring, and the hydroxyl radical concentration that we don't know. And this actually gives us a direct way to try to estimate hydroxyl radical concentrations. And so one of the bonuses of this field campaign is that we got really nice estimates of the OH concentration, the vertical profile, 4 to 7 times 10 to the 6 molecules per cubic centimeter, is exactly in the region that we expected. So that was good, and that's another thing that we use to test the models. The other thing is that we need to extrapolate these measurements down to the ground to get what the flux is at the ground in order to compare that flux to the emission model. Okay, so when we report fluxes from the aircraft, we're always extrapolating them down to the ground based on these estimates of OH. Okay, so now a couple more things we do with the fluxes. So this is, now we've got to the point where we've measured the isoprene surface fluxes, and that's shown on the left, and you can see that we get high fluxes over the oaks and less in the valley, but and the pattern was fairly similar to what we saw for concentration. But when we do modeling of isoprene flux, we actually use what's called a basal emission rate times a temperature dependence factor and a light dependence factor. And so one way to compare the models to the measurements would be to actually compare the fluxes directly to the modeled emission rates. Another way is to actually derive basal emission rates from the aircraft measurements by taking the airborne flux that we measured and correcting it with the expected temperature and light dependence to standard conditions that are used to drive the model of 30 degrees Celsius and 1,000 micromoles per meter squared per second of photosynthetically active radiation. And so we're actually going to compare them both ways. We're going to use these basal emission rates that are derived from the airborne fluxes and compare those to the basal emission rates that are in the model. Okay, and then we'll also do a comparison of actual fluxes from the aircraft and fluxes from the model. Then when we do that normalization, for light and temperature, this is what we get for the basal emission rates. And we can see that the patterns look pretty much the same, except that in some cases, like here, it was cold that day when we flew over it. So the fluxes were relatively low, but when we correct them back to standard temperature of 30 degrees, we get much higher levels. And conversely, it was hot when we flew over this region. And so when we get basal emission rates, they decrease. And in fact, in thinking about looking at where isoprene emissions are likely to be high in California, it's much easier to think about the basal emission rates because that tells us what the emission capacity is for those landscapes. Okay. So using Aircraft Isoprene Flux to verify and improve emission models, we're now going to examine the 2-kilometer resolution flux data, that's the wavelet data, and we're going to test the models and the model inputs. So the basic things driving the models are land cover driving variables, so the vegetation that's on the ground, the leaf area index, and the meteorological driving variables, the light and temperature that cause emissions to change. And the emission models also contain a variety of other things. The emission factors are expected from the plants. There's some short-term and long-term emission algorithm corrections for temperature history, for canopy environment, and things like that. I'm not going to go into a lot of detail on that side of the modeling. But from our perspective, after doing this study, but even going into the study, our expectation was that the most uncertain input was likely to be the landscape-weighted emission factor database. So when you run these models, you start with an estimate of what is on the ground in terms of oak trees in particular, but other vegetation as well. And there were 3 different databases that we were looking at in thinking about the land covers. One is the BEIGIS model that uses the GAP land cover database for oaks. And this was put together of order 2 decades ago, I think, and Klaus was largely responsible for putting that together with a lot of work done by some contractors and researchers that did projects for the Air Resources Board. And it was a huge effort, and it is still the basis for the California Air Resources Board's model. And then there was the Megan 2.0 model, which was put together by Alex Gunther using what they call land cover 2.1, which is also based partially on the GAP database. It's called WestGAP, with additional information from forest inventory analysis. Sorry, I forgot a Y there. And that's a U.S. Forest Service product. And then the third one is Megan 2.1 model with their land cover 2.2, which is actually a really different approach to getting at the land cover. It's for the first time using remote sensing based data and the National Land Cover Database. Okay. So thinking about the input variables for a moment, this is the database that's used for input to drive the model. It's the WRF temperature. And this is just showing an animation of how variable that those temperatures are. And one of the things I want to point out is where we flew is where the oak trees were, basically around the valley. And right on the edge of the valley, you have very strong temperature gradients is what I want you to pick up from here. And it's a very dynamic situation. And so it's important to realize that the way we take data out of the WRF temperature model and then apply it to the emission model matters a lot. So this is showing what happens at different spatial scales of averaging. And I'm sorry if this is a little light and hard to see, but basically we're going from the observed temperature at 3-kilometer scale from our racetrack and here and here. And then this is looking at the 8 by 8 kilometer averaged WRF temperatures, and then going down here, you're looking at 20 by 20 averaging and 40 by 40 kilometer averaging. And you can see that as you get to larger and larger scale averaging, we're further and further from the actual temperature that was driving the emissions. So it's important to average the inputs, particularly the temperature input, at a reasonable scale. And what was used for the modeling was actually a 4 by 4 kilometer average of the WRF output. So this is 4 images showing you the different land covers that are being used to drive the model. The upper left is the oak woodland distribution in the GAP database. And that is fundamentally what's the starting point for the BEIGIS land cover database, which is shown up here on the right. On the bottom right is the Megan 2.0 land cover, which again was West Gap with forest inventory analysis information added in. And then in the bottom left is the Megan 2.1 model with the land cover 2.2 that is derived from satellite observations. And you can see that they're fairly different. And so we're going to fly through each of these and we're going to show our flux measurements overlaid on each one. And so first of all, there's the GAP database of where the oaks are, and that's where we measured fluxes. So I want to say very proudly that we did a great job of covering where most of the oaks are in California. And we had 40 hours of flight time to do it in. So we managed to do it without having any downtime on the instrument, which was kind of amazing. So we actually got fluxes over this whole landscape. And you can see that for the most part, where there are oaks in the GAP database, there are relatively high emissions. But if you start looking at the details, you see some interesting features. So in general, the GAP database is telling us where the oaks are, and that's good. And this is the BEIGIS model. And so these are the fluxes measured compared to the BEIGIS model. And again, we're doing a pretty good job. But if we start looking in a little bit more detail, you might see there's some areas, for example, flying over the Central Valley, where there's a little bit of isoprene emissions, but the BEIGIS model doesn't have any there. You can also see that there's some areas that we might fly through, like over here, where the BEIGIS model says there should be fluxes, significant emissions, but we didn't measure any. Okay, and so when we start looking in fine detail, we can see at a 2-kilometer spatial resolution, each of those points is 2-kilometer spatial resolution, you can see some little differences. Now, when we go to the Megan 2.0 with land cover 2.1, again, this is the WestGap database that has the forest inventory analysis information used. You can see that the distribution of isoprene emissions is predicted to be a bit different. This was BEIGIS, and there's basically nothing in the valley, and it's really focused more on the foothills. And here, it looks like the emissions are more smeared out. It turns out that the averages of these two over the state is pretty much the same, but the distributions are quite different. So when we look at the fluxes here, we can see that there are actually areas where they agree well and some areas where they don't agree well. We can zoom in again, and we can see that for example, here in the valley, there are areas where the model would have predicted higher emissions, but we didn't see such high emissions. And again, the distribution doesn't match perfectly, but it's pretty good. Now, when we go to the next one, this is the satellite-derived data. And what I really want you to take away from this is that the satellite-derived one is just shockingly good. It's really surprising. And when we look in detail, for example, we can see that over some of these regions where the BEIGIS and the 2.1 land cover said that there should be emissions. The 2.2 land cover says that there shouldn't, right here, and the plane confirms that. Okay, and so we can also see that the gradations in the hills here are pretty well captured by the model, and it's hard to get a real sense of how good it is just by doing these visual comparisons. So what we wanted to do then was find a way to average the measurements and the model in an ecosystem specific way to show how good it is or how bad it is. And so we relied on ecoregions that were defined by the US EPA. And this is a map of those ecoregions. And basically the yellow ecoregion, it's referred to mostly as region 6 in here, is where most of the oaks are, and that's where we mostly flew over. But they're classified a little bit differently. And so we took all the data from the aircraft fluxes and and from the models, and we averaged them by ecoregion. And when we do that, this is a scatter plot comparison of the measured BERs from our flights versus the BERs that are in the Megan 2.1 model with the land cover 2.2. That's the satellite derived. And the R squared on this is 0.79, a slope of 1.09, saying basically that the BERs in the model are within 10% of what we measured, which is astounding. To be honest, that is incredibly good, and I was surprised because we didn't necessarily expect the models to be quite that good. But that was really good news. So when we compare to the current CARB model, which is using the BEIGIS land cover, an older, slightly older land cover, we see some interesting things. So this is actually flying along where the plane was going, and you can see that when the emissions go up, that means we're basically over oaks, and when the emissions go low, we're not over oaks. And most of the time, the measurements and models are actually agreeing pretty well, but there are a few areas, like this one, where the land cover overestimates the amount of trees there, and so the model gives too high a flux. Or here, where the land cover underestimates the tree cover, and therefore the model gives too low a flux. So there's a good agreement in most places, but it's clear that the land cover 2.2 is more accurate, and the discrepancies can clearly indicate where the land cover needs improvement. Right? It's a little bit of a busy slide, but what I wanted to say with it is that we also looked at the sensitivities of the model output to its driving variables, which are generally leaf area index and temperature and light. And this is examples for temperature and light. And the main point from this is when we increase or decrease the temperature by 20% driving the model, we get a fairly small change in the emission, and that basically the shaded area in red is showing the whole range of plus or minus 20% sensitivity for temperature, or in green here it's plus or minus 50% leaf area index. And what you can see as you fly through the model is that those aren't the variables that are determining whether the model and measurements agree very well. It's really about the landscape. It's about whether there are plants on the ground that are emitting isoprene. So the sensitivity runs show that the meteorological variables are not the largest source of error, and that the largest measurement model disagreements are due to model land cover. Now, when we go to look at the measured emissions versus the CARB model, and so this is the actual model that's being used for the state implementation planning. This is the actual flux now, not the BERs, but the actual flux that was measured versus the flux that was calculated by the model. And I'm sorry that's labeled wrong. It shouldn't say Megan, it should say BEIGIS. But in any case, you can see that there's a big outlier up here. And so there's an area where the Megan model, or the model said the emission should be much higher. But when we zoom in, we see for most ecoregion averages, we actually get pretty darn good agreement. The one-to-one line is here, and this is the best fit line. The slope is 0.81, so it tells us that on average, the model's actually within about 20% of the measurements, which is spectacularly good. Okay, but we see basically that the current version of the model, the CARB model, BEIGIS underestimating ecoregion average measurements by 90% of the whole data set. For 50% of the ecoregions, the agreement between model and measurement was within 50%. For 21% of the ecoregions, the model was overestimating. For 29%, it was underestimating by 50% or more. Also, the agreement was generally better for ecoregions with more extensive measurements. So when we put all the data into buckets by ecoregions, some had a lot more extensive coverage than others. And so our statistics were poorer for some ecoregions because we simply didn't sample them as much. And that's where the bigger disagreements between measurement and model actually occurred. Okay, so now I'm going to give you a slight different perspective. So we've been talking about this aircraft that's been flying around the state, flying really over the areas where there are oak trees mainly. We've been doing transects across the valley to get to where the oaks are. But at the same time, we had vertical profile measurements on this tall tower at Walnut Grove. And that tall tower, again, is about 20 kilometers south of us. And those measurements were going on continuously. So we could actually see the diurnal cycles both in the vertical and in and we could actually see when there's daytime upslope flow and nighttime downslope flow, how that changed the concentrations that were being observed. We had a PTRMS there doing vertical profiles every 10 minutes for about 20 different masses. And this is how the setup looks at the tower. So we had inlets at 525, 394, 262, 131 in 10 minutes. In 10 meters. And every 10 minutes, we looked at all of those heights. And we've got data for ozone. This is where Mark Fisher has been doing all his work on greenhouse gases. And so what does that data look like? This is average over about 40 days of the isoprene concentration. And what we're looking at here is the isoprene as a function of altitude and time of day. For perspective, I put a plane where their plane was flying. And so you can see that even though the plane is not seeing significant isoprene, right near the ground, there still is some isoprene. And so at that scale, if there were relatively small emissions at the ground that were causing some increases, the plane might not see it. It has to be a pretty significant source for the plane to see it. Another really beautiful thing that we can do with this data is we've got timelines. And here we're showing timelines of a number of different things. One is the isoprene concentrations, and they're shown at 10 meters through 525 meters. And you can see those blue spikes are basically the 10-meter data. Then you can see below that the methylvinyl ketone and methacrylin. And those are isoprene oxidation products. And you can see the pattern's very different from isoprene itself. And we're going to get into why. And in the bottom, we've got temperature measured at the different heights that's corrected for altitude, basically making a product that we call potential temperature. So when the potential temperature is the same at all the measurement heights, that means that there's strong vertical mixing going on. And when it's very different, when the potential temperature is much lower at the ground, that means we've got an inversion, and it's very stable. And so what you can see is that during the time when things are well mixed, then we also have well mixed concentrations. See, MVK methacrylin is pretty much the same at all heights, pretty close, and isoprene is too. But as soon as the inversion layer starts setting up right there, you can see that there's this emission source of isoprene at the ground that's just building up really to high levels in that inversion layer. Also, you see that there's a nighttime increase in MVK methacrylin, but it's not at the ground, it's up high. It's above the 131 meter inlet. And that is because air is flowing back down from the mountains surrounding the Central Valley. And as the airflow comes back down from the Sierras into the valley, it's actually not coming all the way down to the ground. It's actually going on top of the inversion layer. And so we call that a residual layer. And that residual layer we found is rich in MVK methacrylin at night. So this is what the aircraft saw flying around between 10 a.m. and 4 p.m. And this is what we see at the tower. And I really want to point this out so that here at the Air Resources Board, you recognize that when we get really high emissions in the oaks that are surrounding the valley, and we go and look for those in the middle of the day at 400 meters, we don't see them over the valley, but at night, the oxidation products from all that isoprene flows down into a residual layer over the valley, and in the morning, it mixes straight down into the valley. So every morning you get this flush of isoprene oxidation products that are flowing into the valley, even though the emissions happened in the foothills that are surrounding the valley. And I think that's really important to be getting right in the air quality models, because it should really have a big impact on the VOC reactivity in the valley and ozone and aerosol formation. And I'm not sure whether the models get this right. Getting that vertical mixing right is actually a pretty hard thing to do in the models. Okay? So just to give a little bit more perspective, so remember the plane was flying right here, and you can see that the isoprene was building up near the ground during the day in the middle of the valley, but it wasn't really getting up to the aircraft height very much. That means that the emissions were relatively small, but they're there. You can see the monoterpenes building up at night, and then you see it mixing up when the vertical mixing starts in the morning. This is what I just showed you with the MVK and methacrylin. And then this is the potential temperature. And so the potential temperature basically tells you that during this time where the potential temperature is the same as a function of altitude, that's when we have good mixing. Here's when we don't have good mixing. And you can see the mixing starts up and then it's well mixed by here. And you can see the impact really beautifully on the monoterpene measurements. And you can also see when the mixing slows down, that's when the isoprene starts to build up near the ground. So these two sort of perspectives are really complementary and useful. So conclusions. We confirm that oak woodlands are the dominant source of isoprene in California. Very important conclusion. We saw that the spatial resolution of the temperature used to drive the models is very important, particularly in the foothills where the oak woodlands dominate the landscape and the temperature gradients can be strong. The largest uncertainty in modeling isoprene fluxes for California is the landcover input. The Megan landcover 2.2 basal emission rates were the most accurate, agreeing with the measured BERs within 9% averaged by ecoregion. CARB's model using BEIGIS landcover showed reasonably good agreement with ecoregion average flux measurements, underestimating by 19% of the whole data set and agreeing within 50% for half of the ecoregions. Okay. One of our, probably the most useful thing for ARB to come out of this work is we're recommending that you update your land cover database and start using these remote sensing products that do a much better job of identifying exactly where the plants are. And then we also conclude that continuous measurements at Walnut Grove complement these aircraft data to elucidate temporal and vertical distributions of isoprene and products in California's Central Valley. And part of the point of that is that doing aircraft flux measurements is really, really useful for verifying these emission inventories, but it doesn't tell us the whole story, and that we need continuous measurements on the ground. The aircraft gives us a snapshot, but it gives us a lot of spatial information. The ground-based measurements can give us potentially vertical profiles, but they also give us temporal information that's really, really important. Okay, so a few statements, maybe wordy statements about promising future directions for landscape scale flux observations from the aircraft. First of all, we did this once. We did it in June, and we focused on the oaks. We got a few measurements over other areas that weren't dominated by oaks simply because we had to fly through them. But we only had 40 hours of flight time, so we had to focus on where the isoprene emissions were high. We think it's really important to verify emission inventories in different seasons, like the peak ozone season later, July and August, and improve emission models for a wide variety of landscapes, forest, agriculture, oil, gas fields, urban, et cetera. And when we think about that, it's also important to recognize that the technology for measuring the VOCs has been leaping forward. And so we used a quadrupole-based PTRMS. That was what was available in 2011 when we were doing these measurements, and it allowed us to measure about 4 different masses, maybe 5 different masses at one time. Newer instruments that are now available use a time of flight mass spec that's scanning continuously over the full mass range, and we've shown in other measurements that are based on the ground that we can actually get fluxes of hundreds of different VOCs all simultaneously. And we believe that we could actually do that from the aircraft. That would allow us to look at anthropogenic VOCs, biogenic VOCs, and potentially other SIMS, chemical ionization mass spec instruments could also be put on the plane to enable simultaneous measurements of a very, very comprehensive array of VOCs that would be really useful for verifying emission inventories, not just from biogenic sources. But also we could be flying through urban areas, over oil and gas fields, et cetera. Another thing that I want to point out is really important is what comes up must come down. Isoprene gets oxidized, all these other VOCs get oxidized. Some of that goes all the way to CO and CO2. Some of that goes to form aerosol, secondary aerosol, but some of it's deposited at the Earth's surface. And we have very, very little knowledge of the deposition rates of all these oxidized organics. But the technology has come to the point where we can start to really look at that and try to understand the ultimate fate of these organics. And so from a scientific perspective, understanding the deposition rates of the oxidized VOC is really important. And we could do some of that from the aircraft or from ground-based measurements with the PTR top MS and other newer SIMS technologies. And also we could expand the scope to look at other species, and in particular, interest to California right now is greenhouse gases. And so the same approach could be used to verify emission inventories for particularly methane, but potentially also other greenhouse gases, NOx, NOx, CO, or other species of interest. So I want to thank you for having me here. And I'm happy to take questions.
Yeah, the second bullet in your conclusions says that spatial resolution of temperature is very important. Based on the measurements that you've done here, what would you recommend as far as the resolution for the model?
Well, I actually think we concluded that the 4x4 kilometer output from the WRF-Chem model was actually pretty good. But it can also be tested against ground-based stations, and that's a very useful thing to do. So there's networks of temperature measurements throughout California that can be used as verification. But if you start averaging over larger spatial scales, then the temperatures that you're using to drive your model in that region where the oaks live could be too far off, and it tends to bias it. So we concluded 4x4 kilometer resolution was pretty good, and yeah. If it could be done at a higher resolution, that's great, but I'm not sure it's reasonable.
Just a follow-up question to that. 2-meter air temperature typically is measured in shelters. The canopy temperatures that will dominate the driving force for the isoprene is going to be different. And how do we reconcile that? Because models gives us 2-meter air temperature that assumes that we're measuring in a shelter, and canopy temperatures are going to be different than that.
So that issue of estimating leaf temperature versus air temperature is something that is done in the biogenic VOC models. And different models actually do it differently. Most of the biogenic VOC emission models have some kind of canopy model within it. So they're estimating what fraction of leaves are in direct light, what fraction are shaded, and also estimating the distribution of temperature across those leaves. And so I must admit that I don't know all the subtleties off the top of my head of the differences between how that's being done in BEIGIS and how it's being done in Megan, but that is something that is definitely directly I'm happy to hand the mic over. Oh, okay. Okay.
Yeah, the BEIGIS model is a little long in the tooth now. It doesn't have a canopy module in it. It treats everything as a big branch. And the underlying land cover data set, the GAP land cover data set, is also long in the tooth. So it's been on my mind for a while.
Yeah. Well, and I would also say that the state of the art has been evolving. And this was a good project to test whether the evolution of the state of the art really was making a difference in improving the estimates on the landscape scale. And certainly, I think what we saw is job, but it can still be improved, and one of the main ways to improve it is actually the land cover. And that's feasible because that land cover is available. It's just work to make it happen.
I was interested in that new land cover piece in the Megan 2.1 because on the greenhouse gas inventory side for wildlands, we've dipped into using another remote sensing derived product from the Land Fire Consortium. So that's those vegetation raster products are based on Landsat imagery and FIA and some of those things. So but just as a reminder that, yeah, we need to update how we do the biogenics. So.
And I would also like to mention that the landscape's not static, right? And so it would be wise to be thinking about it in terms of having landscape inputs that can be updated with time. And the best way to update them with time is with remote sensing data. They're actually telling you how the ground has changed. For example, you can imagine the big fire model, you're missing something pretty significant. And so the landscape in California is shifting. More questions? Chris.
Hi, I know it wasn't really a focus of your talk, but it was interesting that you got hydroxyl concentrations, and you said, what, 4 to 7 million, I think? Was there any interesting pattern in terms of where they were higher or lower?
So the only places that we could actually get an estimate of OH is when we did the racetracks, when we did basically vertical profiles. So we did flux measurements at different heights, and we only did that 3 times. And twice we did it in the same location. So I don't think we got enough information to say something about the difference in OH from day to day, for example. But it's a potential really interesting way to try to go and get average OH concentrations in the vertical profile in the future. I mean, I could imagine a campaign that would be really focused on that using isoprene and a series of other tracers.
Isoprene would be the best one now, wouldn't it, in California?
It's always better to have more than one. I know it's scary having more than one thermometer because you never know what the temperature is, but if you do it with enough different species that have maybe different reactivities, you can have more confidence of what your air levels are, put it that way.
You mentioned you did these flights all in June, and that obviously that isn't the high ozone season. Would you expect significant differences in, say, August and September?
So it's a really interesting question, and there are definitely going to be differences in the fluxes. But when we take those fluxes and we normalize for temperature and light, and for all the other factors that we expect to change in the phenology of the plants, we hope that what we're really testing is whether the basal emission rates, the BERs, that are being used for the model are right. It's quite possible, though, that there are going to be some differences between June and August. For example, this year, when the drought is really extreme, it's possible that that extreme drought is going to reduce the basal emission rates for the oaks, right? So those kinds of things we can't address with our current data set, but I think it would be really wise to do it again in July and August. We did it in June partially because that's when we could get the plane, right? So I think John Seinfeld's group had the plane in August that year. So John got priority. But I think it's very reasonable to try to go back and do it in July or August. One, potentially look at sort of these drought stress effects, and two, the emission should be much higher at that time. And actually, could measure them even more accurately if they're higher. So the higher the emissions are, the better measurement we get.
We have a question from the internet.
Let me read this question to you.
Who it's from?
Yes, it's from Megan McKay. Yes, you know her well, I think. Yeah. Thank you very much, Professor, for your presentation. Can you explain why, when looking at the Walnut Grove Tower, isoprene seems to build up, or is it measurable, only during the well mix time?
Oh, it actually wasn't during the well mix time. It was, I'm sorry if I said that poorly, but it was at the end of the well mix time. So here's the slide. And so it's well mixed through this period, but then the emissions are highest when the temperature is highest. And you can see where the concentration starts to really build up. It's right after the mixing starts to slow down, or right when the mixing starts to slow down. It's right around here. Okay, so I think that's basically an indication of the isoprene emissions are still going on while the mixing is slowing down. But when the mixing slows down even more, the isoprene emissions basically turn off because there's the temperature is lower and there's less light. I did have, well, if we get to it, I could go on because I prepared a few slides that show a little bit of data of methanol and methane from the flights that may be interesting. But we'll see if there are any more questions first. Yeah.
Just sort of a follow-up to my first one. How confident are we that we understand the effect of temperature? Because you pointed out in this, if you sample in August, September, you'll need to correct for temperature.
So the temperature algorithm for how isoprene emissions change as a function of temperature is actually one of the best studied features that goes into this model. So a lot of people have taken leaves, put them in a cuvette, and changed the temperature and verified how the temperature affects emissions. And I think that is probably one of the more certain parts of the model, actually. Our ability to estimate what the temperature of the leaves are may be more uncertain, right? So the actual temperature dependence that's in the model, I think, is really good. Our ability to say what the temperature is that's leading to the emissions is the hard part. So that's the averaging of the WRF temperature fields and then dealing with these canopy effects that were asked about just a little while ago to see if we're really getting the temperature right at the leaf scale where the emission's happening.
I just wanted to ask a question. I've always said today to the boredom of the audience that the land cover models are very, very critical. I'm real glad to see it actually is, the science seems to agree with it. You also make mention of collecting actual video data with GIS.
Yes.
Has that been turned into a paper or a product?
No, it's mostly been used for when we're thinking about interpreting the data. Actually, Abhinav Guha used it quite a bit in trying to understand the variations in methane that were observed. But we haven't tried to publish anything with the videos in it, but all that data is available. It is available. But if I may, could I go on for a couple minutes? I just love it. You've got the mic, and I don't know if anybody wants to stay on. But here's methanol. Methanol is really interesting because it's the dominant VOC in California. Much higher concentration than isoprene. And you can see that the concentration of methanol was really high in a few locations as we flew around, particularly along the eastern edge of the valley, but also when we flew over the valley. These black points are basically where we flew high, and so when the altitude, we were above a certain altitude, we just disregarded the data so it didn't confuse what you were looking at on the map. But you can see actually when we flew through this area, fairly high methanol levels, and here also. And the interesting thing about that is the pink is where all the dairies are, And there's a big triangle right here where there's a large beef cattle operation. That's the Harris Ranch, and which some of you may have noticed as you drive down Highway 5. So the maximum concentrations of methanol in the Central Valley often exceeded 10 parts per billion, which was really high. We actually measured fluxes also. So what you can see here is the difference. This is the concentration distribution. This is the flux distribution. So the concentration isn't always highest where the emissions are highest because methanol has a long lifetime. And so you can see now that the fluxes actually, when we flew over these dairies, were the highest that we observed pretty much anywhere where we flew over the dairies. And there are a few other places where they're relatively high. But over here, where concentrations of methanol were really high, we actually saw, in some cases, the blue is actually deposition. So methanol was getting up to high enough concentrations that it's actually being deposited on the forest downwind. And one of the reasons that I think this is really interesting and useful is that methanol, I think of as just an indicator of all the various stuff that's coming from the dairies. And so the flux measurements of methanol over the dairies can potentially give us a scalar to scale against what we know is coming from the dairies with methanol and get an idea of the emission inventory for those things. And if we zoom in to that picture, we can see, again, these are the flux measurements. The pink dots are all the various dairies, and you can see the fluxes get really large, and then again, as we come up to this beef cattle operation at the Harris Ranch, we get very large emissions. So again, this is showing the different spatial patterns for the flux and the concentration. So the flux tells us where the emissions are. The concentrations tells us where those emissions go. All right. We can also see something else that's really interesting. So we had methanol measurements now in these three different campaigns. One is the Walnut Grove vertical profile. One is the aircraft distribution that I showed you. And one is at the citrus site where we did measurements for a full year. And what's amazing is that you see really different pictures depending on where you look. These are average vertical profiles. So at Walnut Grove, methanol was highest in the middle of the day. And then at citrus, it was actually highest in the late afternoon. And the difference is the proximity of these sites to the dairies and which way the wind's blowing. So just looking at methanol concentrations in one location doesn't give you the complete picture. I also want to point out the difference in scales here. So the concentrations in red here are about 12 to 20. In red here at Walnut Grove, it was just going up to 8 ppb. And here at the citrus site, we're going up to 25. So we get much higher concentrations of methanol down in this region than we do up here. Okay, and that's basically because of the concentration of the dairies. So this is methane measured from the aircraft. And what you can see, for the most part, is, at first glance at least, the methane on the left here has a spatial distribution that is pretty similar to the methanol. And so you get methane building up on the edge of the valley here. You see it high as you fly over the dairy regions, and that matches sort of what you see for methanol. Methanol is also high in other regions, and one thing to point out here is that where methane wasn't very high, one thing to point out is that methanol isn't just coming from the dairies, it's got a lot of sources. And in fact, methanol is a dominant emission from crops and from other kinds of plants. But it can potentially be used as a tracer, and we can look at the methanol to methane emission ratio in plumes as we fly over these areas to help us determine where that methane came from. So Abhinav Guha, as part of his PhD thesis, actually looked in more detail at a lot of that methane data. And so unfortunately, this is colored differently. Now the blue dots are the dairies. The yellow dots are landfill. And the pink areas are the oil and gas fields. And so these are just showing a couple of flights that we had. This information is in Abhinav's PhD thesis. It hasn't been published yet, but he is working towards that. And you can see that downwind of all these dairies, well, over the dairies you had higher concentrations, but downwind you had really high concentrations here, and also a bit up here, high concentrations. But that was in one research flight. In this research flight, as we flew over the dairies, you can really see the buildup. You can also see enhancements over the oil and gas fields here. And if you look in very close detail, which I'm not showing here so much, we do see enhancements when we fly directly downwind of some of these landfills as well. So we can start to get an idea of the distribution of sources from the aircraft, and we think this is actually a really valuable approach that might be utilized in the future to verify the methane inventory for the state. I think I'll stop there. Thank you very much.
Well, thank you, Professor, and thanks everyone for coming. And the presentation is posted. I've looked at it several times since yesterday, and you should too. It's useful.